Hello, everyone, and welcome to today's webinar with Citadel, using Nomad to deploy and run any application on any infrastructure with one workflow. Please feel free to type your questions during the webinar. We compile all questions and answers at the end of the webinar and send the results to everyone registered. This webinar is recorded, and the recording will be made available after post-processing, usually within about 2 days. With that, let's go ahead and get started.
Hello, everyone. Thanks for joining us. Like Amanda said, today we're going to talk about sort of a brief overview of Nomad, then look at some of the new features of 0.6 with a live demo, and then hand it off to Caius from Citadel, who's going to tell us a little bit more about their use case. So for a little bit of context, my name's Armand Dadgar. I'm one of the founders and CTO of HashiCorp. I'm going to take a wild guess that most of the folks on the webinar are relatively familiar with HashiCorp, but for those who aren't, we make a suite of products sort of looking at provisioning, securing, connecting, and running applications. And so thinking about the different challenges in application delivery and decomposing it into these 4 pieces. So we make a total of 6 different tools. People are probably most familiar with Vagrant, which is our development environment tool. We also make Packer for building machine images, Terraform for provisioning, Vault, which is our security-oriented tool for secret management, Nomad, which we'll be talking about today, which is our scheduler and designed to run any type of application, and lastly, Console, which helps glue everything together with service discovery. So what I really want to focus in on today is giving a brief overview of Nomad for those who are new to it, and then drill in on some of the new features that are coming with 0.6, and then do a live demo of some of those features, just because they're pretty awesome. So starting right off with Nomad, when we talk about Nomad, we really describe it as 2 things. It is both a cluster manager and a scheduler. And so when we talk about that, I think the key one here is really what does it mean to be a scheduler in this context? When we talk about a scheduler in the abstract, the goal of a scheduler is to map some set of work onto a different set of resources. And this applies into all sorts of different domains, right? So one particular domain is a CPU scheduler, for example. So every operating system, every phone, probably at this point every video game console has a CPU scheduler. And the goal of this is to map some set of work, which is threads, effectively processes and virtual threads within them, onto a fixed set of resources, which are the actual CPU cores, and to do this dynamically. And we need to do this because we have typically way more work, way more threads than we have actual CPU cores. And so we needed a scheduler to do this sort of dynamic mapping. And so over time, the CPU scheduler is free to change what set of work is being allocated to what set of CPUs, and this gives us the illusion that everything is running in parallel on the machine. And so CPU scheduler is really just one type of scheduler. In reality, schedulers sort of rule everything around us, and we see them kind of everywhere. So CPU schedulers, they map one type of work, which is threads, onto one type of resource, physical cores. If we think about larger systems like Amazon EC2 or OpenStack Nova, they are effectively giant schedulers that are mapping virtual machines onto a set of fixed hypervisors. We have query engines, things like Hadoop Yarn, which are mapping queries like MapReduce onto the client nodes that can execute them. And then lastly, when we talk about cluster schedulers, things like Nomad, we're mapping a set of applications onto a set of fixed servers. So this is really what we mean when we talk about Nomad being a cluster scheduler. And so what does this look like sort of more visually? It starts by having the one set of resources, which are the Nomad clients. These are actual just machines that are connected into the Nomad servers, and a small set of Nomad servers that are acting as the coordinators for the fleet. And so as users, we were able to submit a job that says, hey, I'd like to run 2 copies of my web server. And then it's Nomad's job to basically find space in our fleet. So it can look through and find available capacity. Some machines may be busy. We've already scheduled applications onto them and they're fully loaded. But the goal of Nomad is to manage this for us. As a user, we're just saying, run 2 copies of this. I don't actually care where it's running in this fleet. So what are the advantages of using a scheduler? There's 3 primary ones. And this is more than just cluster scheduler. This is sort of schedulers in the abstract. The first one is higher resource utilization, right? Because we're allowing this dynamic layer to pick what's running where, it's able to make more intelligent decisions than if we just did a static mapping. So we're able to, for example, bin pack multiple applications onto the same hardware to get a higher density of utilization. we get this nice decoupling of work from our resources, so our applications aren't making a whole lot of assumptions about the underlying fleet. But what this frees us up to do is to deal with things like masking of failures. So if a machine in our cluster dies, or we lose an entire rack, an entire cage, Nomad is able to mask that from the application because the app is decoupled. So it can dynamically move the applications onto another set of hosts that are currently healthy because of this decoupling. And lastly, we can get a better quality of service. We can use things like priority systems and preempt low priority work when high priority work comes in. We can use quoting. We can restrict the amount of resources particular jobs are able to use. And so we're able to use these different levers to increase the overall quality of service. And so there's a number of these sort of sub-techniques, right? For resource utilization, it's primarily bin packing, so trying to fit as many apps onto one machine as possible. It's oversubscription, so this is things like, assigning more resources to the applications than the physical machine actually has, and then masking it when machines go over. So very commonly, this is done when we swap memory, for example. So operating systems will typically allow apps to over-allocate memory, and if they actually use that memory, we'll move that memory onto disk and hide it from the application. And then we can do things like job queuing. So if we've exhausted all of our resources, we can queue up future work, so the moment resources free up, we can start executing right away. We talked about the decoupling. The key here is really that abstraction and the API contract. It allows us to do things like mask hardware failure and move things around because we're able to maintain the same abstraction as we move between different hosts. And this really comes to having a well-defined contract between the user and the system. And lastly, this depends on independent packaging. So some of the value of things like Docker is that now we don't care, is the underlying host RHEL, is it Ubuntu, is it some other type of Linux system? We have this packaging construct that's now independent of that host, and Nomad's free to move it around. And then in the quality of service, like I mentioned, there's priorities. This allows high priority work to take precedence over low priority work. There's resource isolation, so making sure one app can't stomp on another, and then preemption, where we can evict low priority stuff to make room for high priority work. And so this technique of using cluster managers and application schedulers isn't particularly new, right? So Google has been relatively well known for talking about using their Borg scheduler since the early 2000s. If we think about EC2 as a large scheduler, Amazon's been running one for well over a decade. And large customers like Netflix and Twitter have also talked about their usage of schedulers. And so that brings us to Nomad. So when we talk about Nomad, it is very much a cluster scheduler. So its job is to map different types of applications onto a fleet of servers. And so when we think about the personas, who's actually using this system, we really care about our developers in terms of how can they easily deploy their applications and make this as seamless as possible. But we also care about the people who have to manage this cluster. So how do we make it operationally simple, make sure it scales so that our operators can run this easily? So here's an example of a Nomad job file. The key kind of goals in the job file is making sure that it's something that's easy to read and easy to write, because this is what developers are using when they think about their application. So here, for example, is a very simple job file to launch a Redis task. So here we're just using a single task, we're using the Docker driver, and we're running the latest Redis image. So it's meant to be very simple to read, very simple to write. Here's a totally valid thing that we could use to actually run Redis, and we're going to run a very similar example like this in the live demo in just a moment. The key goal of the job file is that it's very declarative, right? We just tell Nomad what we want to run. In the last case, we just specified we want to run this one Redis container. And what this lets us do is sort of free the end user from determining where something should run, so they don't have to care, is there one server, 10 servers, 1,000 servers in our fleet? That's not their problem. They just want one Redis instance. And so this lets Nomad take over the where and the how, right? The monitoring of the process, the deploying it, what happens when that machine fails, all of those things become Nomad's problem and not the user or operator's problem. And in this way, what Nomad is really doing is abstracting that work from the resources. The developers, the users of Nomad, they're specifying the work in the form of these job files where they say, I need 1 instance or 50 instances of an app. And then on the other side, Nomad is managing its own fleet of resources. And so when we talk about sort of mapping this work onto the resources, there's many different types of resources and work that we may want to manage, right? So on one side, there's different operating systems that we may want to support as landing targets. So Nomad runs across Windows, Linux, BSD, Solaris, Darwin. So almost any operating system type can be used as part of a Nomad cluster, and they can be mixed clusters. You can have 50% Windows, 50% Linux in one cluster. And then on the workload side, there's many different types of workload. You might have a long-running service like a web server or an API server. You may have short-lived batch work that just needs to run to completion and exit. There may be periodic jobs, so maybe a weekly or monthly billing roll-up. And then there's system agents, so maybe a monitoring or logging agent that's supposed to run on every machine in the fleet. And then when it comes to packaging and actual execution, there's many different containers, if you will, that we might want to execute. So in true container land, where our workload might be Docker-based or Rocket-based or LXC-based, and it's containerized natively. It might be a virtualized workload, and Nomad's able to use QEMU and KVM. Or we may just have things like static Go binaries or fat jars, and we can just run those natively with Nomad. So Nomad is able to implicitly containerize our app for us using the underlying C group primitives and isolation primitives of the operating system. It'll basically wrap our static binary and run it in an isolated environment without us having to pre-wrap it in a container format. And so the goal from the perspective of the developers and the end users is that they just think in terms of declarative jobs. They don't have to think, what state am I in and how do I get to the next step and write the imperative logic. They only have to specify what they want the end state to be, and Nomad figures out how to get there. And then these job files can live alongside the application itself, right, in sort of a true infrastructure as code approach. So you can write your application and in the same folder have your Nomad job file for it. Of course, Nomad isn't the only piece that you need to run an actual application. Your app probably has configuration and upstream services and database credentials it needs. So there's native integrations with console to do health checking and service discovery, native integration with Vault to do secret management. And this really speaks to Nomad's approach, which is how do we compose with other existing pieces of infrastructure as opposed to trying to be a full-on platform with all of the bells and whistles. And the real goal here as we think about using Nomad within an organization is how do we empower our developers by decoupling the work of operators, right? So our operators can set up and stand up Nomad and provide it as a service to the developers who can then submit their job files and interact with the system in a self-service way. So now the flip side of it, if we have our developers who are submitting their work, is our operators who are actually standing up and running this thing. And so one of our big concerns was how do we make sure the system is operationally simple and scalable enough that operators don't have to babysit it. And so for us, this comes down to a number of approaches. One, Nomad is a single binary. So whether it's running in client mode or server mode, it's just a flag to the same binary. It has no external dependencies, so it does all of its own coordination, all of its own state management. It's highly available out of the box, and it has multi-data center and multi-region support as well. So no extra plumbing or glue is necessary, whether you're in one data center or 50 data centers and you want an HA setup. All of that is just the same binary, same setup. The next step for us was really figuring out how do we accelerate its maturity. And so for us, this really started with a few things. One was looking at how do we build on our existing experience. And this was really pulling in things like Surf, which has a bunch of mature libraries and gossip protocols for things like membership, failure detection, event broadcast. And we really learned a lot about how do you do large-scale clustering of a system. And on the other side, we really learned a lot from the design patterns of systems like Consul, as well as how to build consensus-based systems. So if we want a strongly consistent system that scales and supports multiple data centers, how do we actually architect a system like that? And luckily, we've learned a lot from running Consul now at individual customers have over 100,000 nodes of Consul running. So we've really learned a lot about what large-scale system architecture looks like with Consul. On the flip side, neither of those systems really bring any scheduling logic with them. And so that's when we turn to sort of the research field to understand what's the state of the art and how do we make that available to our users. And so primarily, we looked at two major groups of research. One was the work out of AmpLab at Berkeley, particularly the work around Mesos as well as Sparrow in terms of how to do low latency batch scheduling. So for use cases where you have thousands and thousands of small batch shards that need to execute very quickly, that's sort of a specialized scheduling approach, as opposed to more long-lived services where you don't necessarily spin up thousands of services at one time, so you can afford the luxury of spending more time to make the right placement. So we spent a lot more time with the research at Google with things around Borg and Omega and what they've done with it. So at the very core, Nomad's scheduler architecture is inspired by Google Omega. It's highly optimistically concurrent, and so what this means is if you have 100 cores available between all of your Nomad servers, so maybe you're running 5 servers, each one has 20 cores, and you submit 100 jobs to the system, Nomad will attempt to place all 100 jobs simultaneously. And so that's what we mean by it being optimistically concurrent. And so this really gives it a massive advantage in terms of throughput of scheduling. And so what we've really spent a lot of time focusing on is how do we optimize the system for both service and batch workload, where with batch, we really care about the speed and efficiency of placement. And with service, we really care about things like the quality of placement. How do we make sure we're not putting all of your web servers on one machine so that if that thing goes down, the whole service is down? So thinking about things like correlated failure and trying to protect you transparently against that, as well as having a pluggable architecture that lets us support different workloads easily. And so what this looks like from an architecture perspective is very similar to console. There's a set of servers that are managing a bunch of clients. The servers perform a leader election internally. They handle their own replication between the servers. And then we can have clients from many different data centers connected in. So here I've just labeled them DC 1, 2, and 3. There's no limit to the number of data centers a particular region can handle. That said, we may want to separate our regions for the sake of failure isolation. Maybe we split it and say we have a North America region and we have an EMEA region, and they have two separate set of servers, and each one is managing 5 data centers. And so we can federate all of this together into one global architecture, but this way we've isolated our failure domains between these regions. And so when we went through the motion of designing the system, we set a pretty high bar for ourselves as the design goal. What we really wanted to be able to do is sort of set that high watermark that we didn't think anyone would hit, so that we would never have to kind of think about Nomad's core architecture as an impedance for a customer. And so for us, what this meant was we wanted to support hundreds of regions, tens of thousands of clients per region, and thousands of jobs running in that region. And so we sort of put our money where our mouth is with what we call the Nomad Million Container Challenge. And our goal here was to say, could we actually launch 1 million Docker containers in under 5 minutes, right? As this sort of, high watermark challenge for ourselves. And so the way we structured this was we had 1,000 jobs, each job running 1,000 Redis containers for a total of 1 million, and ran this on 5,000 machines in GCE, spanning 3 different regions, right? And what we see is that Nomad, in fact, can do it. And so what you see here is 3 different lines. The leftmost line is the scheduler actually deciding where to place the job. The next line, the gray line, is Nomad notifying the client that, hey, you should be running this container. And the third line is the client acknowledging that the container is now started and running. And so what we see is that Nomad actually finishes the scheduling of all 1 million in under 5 minutes. And then shortly after that, in under 6 minutes, all 1 million containers are actually running. If you look very, very carefully, you can actually see that the orange line goes slightly above 1 million. So we actually schedule a little more than 1 million containers. And what's happening is, on a scale this big, we're just encountering actual hardware and software failures. So as Nomad is running and launching all of these containers, some small percentage of the fleet either is encountering network issues, or at the time we discovered a bug in the Docker runtime where we were launching so many containers at once that we were able to crash Docker. And so for some set of the fleet, Nomad detected that host was lost and migrated the containers onto the other host that had available capacity. So we can see even during the course of this benchmark, we're incurring failure and routing around it and still hitting the 5-minute mark. And so as we finished this, as we sort of published the results of this, the universal sort of reaction was, why would you ever need anything like this? Like, this is sort of an obscene scale to actually design for. And for us, the quote that sort of brought to mind was the famous Bill Gates quote, 640 KB ought to be enough for anybody. And the way you have to think about it is there's this co-evolution of what our actual systems allow with what the applications can leverage, right? And so an example of this is, what's the type of applications we could build if we had databases that could only do 1 transaction a second? Well, it's very different than the type of apps we can build if the database can do 100 transactions a second, or 1,000 or 10,000 transactions a second. So the infrastructure itself is limiting how we think about what the applications are able to do, right? So back then, 640K was enough because all we were running was these very textual-based interfaces that were doing very primitive things. So of course we didn't need more than that. But as we had access to more hardware, more CPU, more memory, we were able to do much richer things. And that's similar to how we think about Nomad. And so what's funny is, shortly after publishing this and getting this reaction, we received a call from Caius, who's going to be talking shortly after me, from Citadel, which is the world's 2nd largest hedge fund, telling us that that was a very cute benchmark, but can you support a workload vastly larger than that? And we were sort of stunned, but we were very excited to get to work with a group that for whom this wasn't theoretical like it was for us as the sort of synthetic benchmark. This was a real world use case for them. And so we worked closely with them on fine-tuning things and setting up Nomad for them. And they basically ran it through its paces, right? So on an 18,000 core cluster, for 5 continuous hours, they sustained a scheduling placement of 2,200 containers a second, which is sort of incredible. And so when we think about Nomad, this is sort of the major components for it. It's like, how do we think about the domain problem as just mapping applications onto servers? How do we make this really easy for our developers? How do we make it operationally simple for our operators? And how do we build it for scale so that you don't have to architect around Nomad? So with that, I want to spend some time now just talking about some of the new features that are coming in 0.6. I think the biggest tentpole is really the way we handle service updates now. So now there's a much, much richer logic in terms of how services can be updated. So particularly, we've integrated with console health checks as well as building in a much more robust deployment mechanism where now we can do things like staggered rolling deploys that are gated on health checks. So you can specify that I want this thing to roll out, 2 at a time every 60 seconds and only if the health check is passing. We can do actual canaries with manual or automated promotion. So you can say, I'm going to just canary 1 or 2 instances of my app running the new version. If that looks good, I'll promote it manually, and then Nomad will continue the rollout. Or you can do full Netflix-style blue-green, where you bring up the entire version 1 and the entire version 2 in parallel, and once you decide to do the promote, you switch over to V2. The other major improvement is dynamic environment variables. So previously, we supported dynamic configuration templates, and apps could source their config file, which was dynamically rendered. Now we can do the same thing with environment variables. Nomad also now tracks multiple versions of every job. And so this combined with the service update features lets us do really rich things like automated rollbacks, manual rollbacks, as well as diffing to be able to see what's changed between versions. There's now integration to be able to use Docker networking plugins, and a lot more that we're just not going to have time to talk about. So I recommend taking a look at the changelog. So when we talk about the service updates, what we're talking about primarily is as we're changing an existing job from running, let's say, version A to version B. So an example might be we have our web app, and we're upgrading from version 1.10 to 1.2.0. And so there's many different methodologies by which we can do this. All of them are controlled by the same update block within Nomad. So the update block lets us control as a developer what we want our semantics to be, how we want to actually do this upgrade. And there's 3 primary approaches that we support now. One is rolling deploy, one is canaries, and one is blue-green. And we'll touch on each of these. So what does it look like to just do a simple rolling deploy? Basically, we specify our update block and just tell Nomad what's our maximum parallelism here. So here we've defined that we have our web group, which has a count of 6 instances. So we have 6 instances of our web app, and we update 2 at a time here. So, and we're just going to do a stagger using the default value, which I believe is 30 seconds. And so what this will look like is the user first launches and says, hey, I want to run web app version 1. The app doesn't actually exist, so there's no reason to do a rolling deploy. Nomad will go ahead and schedule all 6 of these things. Then at some point, the user comes along and says, hey, I really want to run web app version 2.0. And now Nomad will move 2 of them and wait until those health checks pass. When those 2 pass, Nomad will then deploy the next 2. And when those finally pass, Nomad will then deploy the final 2 instances. And we'll now have completed the upgrade to version 2. Now let's say we didn't want to right away replace the instances of our app. We want to do a canary and a manual promotion. So all we would do is extend that update block now and add a canary. So we might say, you know what, I'm going to roll 2 at a time, but I'd like to canary one of them first before triggering this upgrade. So this changes the flow slightly. So again, the user submits their web app, and Nomad has version 1 running. And now they'll come along and submit web app 2. And what will happen is now we leave all 6 versions of V1 running, but now we have this version 2 canary. So the user can now play with it, test it out, make sure V2 works as they expect, check their various telemetry systems, and then come along and issue a promotion. And so the moment we issue a promotion, we can turn off 1 instance of V1, so now we're back to running 6, and Nomad will flip into doing a rolling deploy 2 at a time with the remaining instances until we've fully rolled out version 2 of the app. The final strategy is blue-green. And to do blue-green, we actually use the same canary command, but instead of just picking, count 1 for our canary, we actually match this canary size to the entire web group. So here we actually had 6 instances of web. We match it and say we want a canary with all 6. And so what will happen is we have web instance 1, we submit web instance 2, and it will launch an entire parallel blue group now. And all of the blue group is considered a canary at this time. Now what will happen is a user will come around and promote this, and at this point we basically are able to shut off the green group, and now we've fully switched over into running the blue group. So what this then integrates with now is the fact that Nomad tracks multiple versions of a job and supports rollbacks. And so we can integrate this with the canary system with an auto revert. So you can actually specify within the update block that if a deployment fails, so if our health checks are failing, that Nomad should issue an auto revert and roll back to the last stable version. And we'll see what that looks like during the demo. Here's a brief example of sort of what a job history looks like. We're going to see a lot more of this in the demo, so I'm not going to spend too much time here. We also have job statuses with versions, so we can actually see what version of everything we're running. At the very bottom, each allocation is marked with what version created it. The next big feature is the dynamic environment variables. So previously we supported a template block that was able to render a dynamic set of configuration. So it could source keys from console as well as services. So you could configure your upstreams or your apps configuration. It integrates with vaults to pull out secrets, so database credentials, TLS certificates, etc. And now with the new environment variable, we can actually populate environment variables instead of just templating config files. So what this looks like is we have our same template block here, where here I'm just inlining the data. And so what we're saying is, feature flag foo is sourced from a key from console, and then we're sourcing our AWS access key and AWS secret key from vault. And at the very bottom, there's a key that we've set, which is env equals to true. And if we set that within a template block, this won't be used as a config file. This will be used to actually generate environment variables for our application. And so now let me flip over and actually demo some of this stuff. So at this point, nothing is actually running. I have, a simple example Nomad file that we're going to use. So actually, we'll come back to this. Let's actually start everything up, and then we can review it. So first, I'm going to start by just booting a console server in the background. So we're just going to start that. And we're going to start a Nomad agent in dev mode as well. We'll just start these things, so we'll let them get going. And so the file that we're going to be working with is this very simple job file. So here it's just a job. We're going to call it example. Here we have our update block where we've specified that we're going to do a staggering deploy. So every 10 seconds, we're allowed to do a roll. The minimum time an app is allowed to be healthy before we consider it stable and able to move on. For the sake of the demo is 3 seconds. In production, for most apps, you probably want to wait a little longer than 3 seconds, but don't want to bore you. And we're going to start by having a max parallelism of 1 and a single canary. And here we've specified auto revert such that if our job deployment fails, it's going to roll back to the last version. I'm going to change this, and we're going to start out by deploying Redis version 3. And here we have a count of 3 things. So we'll start, we shouldn't actually have anything running, so I'm going to run the plan on this file. And what we should see is basically we're going to create this job. So at this point, there is no example job in the system. And so if we were to submit this to Nomad, it's saying it's going to go and create 3 instances of our cache. So let's just go ahead and run it. And now if we come and ask the status for our example job, we should see that we have a deployment running. So here we can see the latest deployment is actually running. It's currently trying to roll out 3 instances of the cache. So down here we can see all 3 allocations have been allocated. So we have machines that we said you should be running this Redis instance. The status is currently pending. It's probably downloading the container and starting it up. And so here so far none of these have been marked healthy. So now it's been a few seconds. Let me just clear and check status again. We're still pending, waiting to download, I guess, Redis number 3. So we can actually come in and grab the status of one of these guys and see what's going on. Oh, so it's still setting up the disk and downloading the container. So Redis is still pending for us. Apologies, I'm on hotel internet, so probably just struggling to download this right now. Okay, let's actually just take a look. Maybe the logs will reveal to us we might have an issue. It's always the challenge with live demos. Let's see. It looks like no errors. We might just be struggling with slow internet here. Oops, sorry. So let's actually just restart it. Try this again. So actually, now that we've stopped it, we should be, this is actually a good opportunity to see the Nomad job history. So now, previously with old versions of Nomad, because we didn't have a job history, the moment we'd actually stop a job, it would disappear. And if you came in and asked for the status of a job, literally a moment after you stopped it, you would see that there's actually, it would just say that the job doesn't exist. But now what we can actually see is when we run it on an old version, we can see the job still shows up, and it's just telling us the status is dead because we stopped it, basically. And so Nomad has basically gone ahead and killed everything. And so if we ask for the Nomad job history, on example, now we actually see that there's multiple versions of it here. And so version 1 was the one we submitted that was actually meant to run it. Version 2 is where we stopped it. We can see that now there's this new thing we're tracking, which is stable, which is like, were we ever actually able to fully deploy out this version and mark it as complete? And so in this case, for some reason, we're unable to deploy it. Of course, a job that you stopped is never able to be stable. And so a new thing that we have because of this history is this P flag that shows you the diff between various versions of the job. So here we can see the diff from version 0 to version 1 was basically we implicitly switched from stopping the job from false equal to true. So we can also use this to see diffs between other things as we change versions. So for example, let's just go ahead and change this job. Hopefully the internet has recovered in the meantime, and we're going to try and run Redis version 3.2. So now we're going to run the plan again. Again, it should try and create this thing because we have no instances of it running. We can see it sees the delta from the last version we have registered, which is version 3, to the new version we're trying to register, which is version 3.2. So let's go ahead and run this again. So our allocations have now been created. It's mapping those onto a group, so we can then go and look at the status. So those have been mapped out on, oops, I always forget the suffix here. I think I've borked my cluster for some reason. Okay. Unfortunately, I think I'm gonna skip part of this demo then. Oh, I forgot I now know the last minute change I made. So when we started console, so one thing sorry, this is a problem with having bad memory. I forgot that I was going to demo the dynamic KV support. So what we've actually done, the reason our job wasn't starting was it depended on this key in console. So we were templating in this key, as an environment variable, just a key called dynamic key, and we're going to source this as an environment variable, and I forgot to set it. So the app actually can't start because there is no value for this dynamic key, which I totally missed. So we're going to actually just set it now. Set it to hello. So now we actually have this dynamic key, and let me actually restart Nomad. Now that we actually bothered to set the necessary key for it. So we'll kill the instance. Just restart this now that we get it into a good state. Cool. So restart Nomad cluster. Cool. Okay, so now Nomad's running, and we've actually set our KV that's required for the job to work. So let's take a look. Version 3.2 looks good. So Nomad plan, it shouldn't actually exist. So let's go ahead and run it. Cool, looks good. Actually got that going. So here we can see it's actually running now. Oof, okay. Pro tips, remember your app's config values. Okay, so now we're running all instances of the cache. So now let's actually change a version of it and trigger a deploy. So now I'm just going to come in here and change the version 3.2. We're going to change it to 3.0. So when we do a Nomad plan on it, we should see now we got a different output slightly. So we're changing it from 3.2 to 3.0. And now what we're going to see is because there's 3 instances of it running, we're actually going to canary this time around. So what we've configured is before we do a rolling deploy, we want to do a canary. So now we're going to just issue the Nomad run. If we come in now, we should see there's a canary version running. So run Nomad example. And so if we look at the very bottom, we'll see there's 4 allocations running, right? 3 of them are running version 0, the initial version we submitted. 1 of them is running version 1. This is our canary. If we look further up, we can see there's a deployment happening, and it's telling us the deployment is currently running. but we require promotion. So we're in a holding pattern until a user does the manual promotion. And within that deployment, we can see eventually we desire that there's 3 instances of it running. At the moment, we have 1 canary, and we're not promoted. So that canary has been placed, it's been marked as healthy, and it's just waiting on us at this point. So now we can come in and issue the promotion. So we take our deployment and we say basically promote all instances of it. So we can do, if we had multiple task groups or multiple canaries, you can do a much more fine-grained promotion and promote different subsets of it. Here I'm just going to mark the whole thing promoted at once. So great, we've marked it as promoted. Now let's come back around and see what's happening. And this is probably taking place so quickly we'll barely see it. Oh, nice. So we caught a little bit of it. So the moment we marked it, our canary is promoted. Nomad started the rolling deploy on the next 2 instances of it. So we can see the next 2 started. This one we just caught right as it was booting up. And then the other 2 were stopped as we went through it. So as we started rolling deploying it, we basically started the new ones, stopped the old ones, and flipped over. And now if we kind of come in, we should see it's totally completed. So all instances are now flipped over to the new version. They're completed and running, and the deployment has been marked as successful. So this was a successful canary and roll. So now if we wanted to see what, for example, the reversion looks like, so actually before we do that, let's do a Nomad job history. And what we should see is great. Both version 0 and version 1 were marked as stable because we were able to fully deploy them and all their health checks passed. We do a -P, we can see basically as we went from 0 to 1, all we changed was Redis from 3.2 to 3.0. So now we're going to try something that basically will force the cluster to fail. We're just going to go in and we're going to change the version of Redis we want to run to a version that just doesn't exist. So we're going to try and roll out version 4.0. And the key here is what we should see is this auto reversion. So Nomad should attempt to roll out the v4 canary. That should fail, and it should trigger an automated rollback back to version 3.0, which is the last stable one. So we'll do a Nomad plan. Again, we can see it's going to canary it. It's going to try and take us from Redis 3 to Redis 4. So great. Let's do a Nomad run. And honestly, this usually happens so fast it's almost impossible to even catch it. So by the time we come back in, yep, we basically see it's already tried rolling out the canary. So canary had tried to run it at v2. v2 failed because Redis 4 doesn't even exist. And before we could even come back and see it, it auto-reverted, created version 3, and version 3 is running again. So an easier way to actually see this is through the job history. So we can see we had version 0 and 1 before, which were stable. And version 2 is when we tried to go to 4.0. And we can see that it was never marked as stable, right? Because version 4 of Redis doesn't actually exist. And so at that point, Nomad triggered an automatic revert back to the last version that existed. And it's back in a healthy state. So if we do the -P, we can see what happened. So here we tried with version 2 to go from 3.0 to 4.0. And that failed. And so we reverted from 4.0 back to 3.0. So now, like I said, one thing that we were doing, the other thing we had done, so taking a quick look, was using this template block for a dynamic key. So here we're setting this environment variable just called dynamic key to the value of dynamic key that we took out of console. And so let's take a quick look at that. So if we do docker ps, we can see our various containers are running. So let's take a quick look at this one. So we'll just inspect a random one, doesn't matter. We'll come up to its environment variables, and what we should see, oops, I just passed right over it. Yep. So we have this dynamic key that's marked hello, which is the value it is in console. So now what happens if we actually change this key? Well, it does kind of what we've done with console template as well, which is the moment the value changes in console, it triggers the template to reload and the app can get a signal. In the case of an environment variable, the only way for the app to get that signal, or to change its environment variable, is to be restarted. Right? We can't change an environment variable once an app is running. So here we're just going to change the console key. Say hi to Caius. Then we'll come around, and if we do docker ps, we'll see that basically everything just restarted. Right? So just a moment ago, everything started restarting because we just changed this key. So we'll grab this again, do an inspect on the new thing that just launched. If we go up, we should see our new dynamic key. It says hi Caius. And so we didn't really have to change anything and describe, how our app should watch console, how it should populate that key, how it should deal with all of this. By just specifying that, hey, this thing is dependent on this dynamic value, Nomad does the sort of full logic for us of detecting the change, re-rendering that file, and then reloading our application. And we have some control over how that works if we want to get more fine-grained with it. But by default, it'll just sort of do the right thing for us. And with that, I'm going to end the demo here and hand it over to Caius. Thanks so much.
Thanks, Simon. Let me, oops. Get started. Sorry, let me just get my presentation set up here. All right, can you guys, can we see the presentation? I'm going to assume that's a yes. Great, so I'll introduce myself first of all. My name is Caius. My name is Caius. I'm from Citadel. I run platform engineering, platform infrastructure here. That's a group that consists of many different functions. We're responsible for Citadel's cloud infrastructure, all its DevOps tooling, logging, monitoring, that kind of thing, databases, filers, and all of our software management tooling. And so what I want to talk about a bit today is, just very briefly introduce Citadel for those who don't know us, and talk a little bit about, so what makes what makes us a little bit idiosyncratic in terms of needs in the compute platform, and sort of show how we've built a next generation compute platform on top of Nomad to really address those needs. Oops. So first of all, Citadel is 27 years old, founded in 1990 by Ken. The asset manager portion of business currently has 27 billion under management. We have about 1,600 employees globally, spread around the world and many different continents. The thing that makes us particularly unique and different from the perspective of this conversation, though, is we're what's called a multi-strat fund, right? So we have many business lines that invest in lots of different kinds of financial instruments. Most of the major asset classes are represented in Citadel across at least one of the business lines, and some of those trade them in those particular assets in very different ways, right? From highly quantitative to more PM kind of style businesses. And what does that mean for the platform team? What does it mean for my team? Is I have to support these multitude of businesses with very different, a big diversity of workloads. They just behave in very different ways. So we have a very wide range of job types that we have to run. Obviously, we, like everyone else, make use of long-running services where, sort of standard kind of thing that you saw, Redis, almond spin up Redis, long-running services that have to be up all the time. And of course, we have our regular batch jobs, sort of end-of-day processing, and sort of most companies would be things like billing and reconciliation and that kind of stuff that has to happen on a periodic and a batch-like basis. Then we have two more slightly idiosyncratic type of workloads. We have the research workloads, which, the retraining of models, which is a workload that we have obviously a number of financial models, and when we get new data or we see changes in market conditions, we may need to retrain those models. And usually that retraining involves a large run on a lot of history of data to retune them on the new conditions. The second class of workload, which is sort of similar, is research workloads. So no surprise, we employ a lot of researchers, a lot of quants, and their job is really idea generation. They come in the morning, they have a great idea, they want to test that out, so they might try it on a small scale to begin with, but then there comes a point where they really need to sort of scale that test out and test their idea on a lot of history. And that involves a very large sort of run of some description to sort of backtest their models and understand how they work. And what really matters here with these last two is completion time. For retraining models, the completion time really drives how quickly you can get that new and updated model to the market, right? And for the research workloads, how quickly you can run that large-scale backtest of the model drives the iteration speed of the researcher. If it's the case, which it has been in many cases around the industry that you have to sort of put a job in and then go home and then come back in the morning and see how you did and hope that it sort of looked good and then sort of iterate from there. You really rate limited the iteration speed of that researcher to one per day, one test per day kind of thing, or maybe a few tests per day. If you can get the results back to that researcher in the time it takes for them to go and grab a cup of coffee and come back to their desk and sort of start poring over the results, that significantly improves their turnaround time on ideas. So really, the time to market and the idea iteration speed becomes critical for us. How does that translate for my team, for the platform team? Essentially, directly translates it how quickly can we perform these computations. It's the speed of the compute platform. So let's actually sort of codify what we need in our next generation compute platform and some sort of more hard requirements. No surprise, Citadel runs multiple data centers, which are stuff full of computers. And we want, first of all, before anything else, we want to make optimal use of that compute capacity. We've already invested in it. They're good computers. We want to really jam as much compute power into that data center as we can. We also have to accommodate large workloads. These large batch workloads or that are coming from researchers or retraining of models are going to inevitably be bigger than your data center, almost anybody's data centers. So we want the ability to transparently burst those workloads into a public cloud provider. I'd say a public cloud provider. The actual real requirement is multiple public cloud providers. Citadel is in many cloud providers for good business reasons, and we want to be able to leverage one or all of them in any of our compute jobs. So we need to be somewhat agnostic to the actual particular cloud provider. In terms of actual hard numbers, we do have some jobs that need to scale from 0 to 100,000 running containers in well under 5 minutes, and we will get 0 warning when we need to do that. It is very unlikely, in fact it isn't likely at all, that someone's going to call you and say they're about to do a massive backtest of some new model. Right, so these workloads will come in with 0 warning where we have to scale up our compute dramatically. Now, of course, we have these sort of research workloads and these retraining models, but we also have all our fair share of long-running services and regular batch workloads, and we want to be able to accommodate those on exactly the same compute platform that we're going to build out to accommodate our research workloads. We want to be able to support containers as a first-class citizen. There's a lot of benefits to doing that, around the ability to work it, especially when we're going to multiple clouds and things like that. It's a hell of a lot easier to ship all the dependencies and everything with the application. So we want to have containers be supported as a first-class citizen. We want to do all this as close to $0 as possible. Every dollar we spend on infrastructure is a dollar we don't return. So we want to really keep the cost of these very large burst workloads down. I think it's worth just spending a little bit of time on cost and how we sort of, what the opportunities are to minimize that cost, because that feeds directly into some of the requirements we have on our choice of scheduler. We make heavy use of what we call ephemeral compute, and ephemeral compute is available to us in the cloud and on-premise. We have two, in the cloud, sorry, if you're familiar with Amazon's Spot market or Google's preemptive market, these offer you the possibility of getting somewhere between 70 and 80, possibly even up to 90% discount on your on-demand pricing. The deal is, of course, that you go to the cloud provider and you say, please give me these 10,000 instances, and they'll provide them to you while they have capacity, but then of course they can take those away at any time should they need them, right? So that's the deal that you do. On-premise, we have a sort of similar idea. We want our scheduler to be able to absorb any available hardware, so any DR hardware, expansion hardware, any underused cores lying around. We want to be able to dynamically expand into that environment and take advantage of that. So we want 2 tiers of service provided to our users. We want the dedicated tier, which is sort of more traditional fixed infrastructure, which is great for running long-running services and things like that. And then we want the ephemeral tier, which is ideal for these very large batch, bursty kind of research and training workloads. So when we started to look around to decide how we would build this platform, sort of obviously the three main, there was Kubernetes, there was Mesos, and then just as we started doing this, Nomad came onto the scene. We did very extensive bake-off between Kubernetes, which is of course the 900-man gorilla here, and Nomad. And the test we did it in June last year, shortly after HashiCorp did their 1 million container challenge. We span up as many nodes as we could on the two schedulers and basically hit them with these kind of research workloads all day long. And what we saw is as we sort of tried to scale Kubernetes up, we got to about I think it was about 5,000, 6,000 cores somewhere in that region, and that's where we sort of started to have problems. We couldn't really feed those cores quickly enough. In Nomad, at that point we tested up to 18. I think we've gone significantly higher than that now. The real killer number for us and what drove a lot of how big a cluster that we could actually maintain was the rate at which we could schedule onto that cluster. And Kubernetes at the time, I think it was about 20 containers per second we were able to squeeze out of it. I think we might be able to get a little bit more than that, but probably not double. Nomad was able to do 100 times that, about 2,500 containers per second. The third sort of factor that we spent a lot of time on was we ran this compute on an ephemeral environment. We actually ran this entire test in a cloud. We ran it on preemptive spot-like instances. And we had significant problems with Kubernetes when we got very large preemption events, when significant fractions, like 20% of the underlying infrastructure just gets immediately pulled out from underneath you. With a bit of tuning on the Nomad side, with the help of HashiCorp, we were able to get that pretty robust in Nomad, and it was able to handle these large, sort of preemption events in the cluster. We were able to replace that capacity immediately with, maybe a different type of instance, and keep going at almost uninterrupted rate. Another thing which is more a qualitative decision was the operational complexity. Just getting the two clusters up and running, and maintaining them at these sort of larger scales, and especially these very high throughput rates, was pretty simple with Nomad, to be honest with you. The Kubernetes side, we had some significant problems sort of keeping it up and healthy under this very high stress. The last thing, which was something Armin alluded to, was the multi-region capability. At the time, Kubernetes Federation was not available. Nomad, it's been multi-region support has been out the box since day one, and it's very much more in line with how you'll see how we treat our global pool of compute. All right, so just a very high-level view of actually what our infrastructure looks like. We have multiple data centers in which we treat as Nomad regions, or data centers depending on the latency between them. Excuse me. And then we have multiple cloud providers, or multiple regions in multiple cloud providers, infer what you will from those colors. There's one sort of, that's our sort of defines our Nomad compute blob. We actually front run the Nomad APIs a little bit with our own compute API, which actually just provides a simple pass-through to the Nomad APIs, but it doesn't do some extra tasks on top of that. It does some authentication and ACLing against our own internal security systems. It applies some policy requirements. We require everyone log in a particular way, so we just sort of make sure that the jobs are set up right before they get submitted to the cluster. That's where we also do a lot of our resource management, that if we see we're running out of compute in one of our cloud providers, we can pump some more compute into there. Or if we have a large preemption event, we can replace those cores with something else. So that's how the user interacts with Nomad. They interact through our own APIs. What does that interaction look like? This is a job file, pretty similar to what Armin showed you. So what happens is that research we talked about, we'll either develop locally, just kind of like in kind of the way that you saw Armin do, and just sort of get up and running, check that they got everything working. They might run a sort of small count of this model A on 100 nodes on-prem, just to sort of make sure that things are working right and working how they're expecting. And then they get to this point where they need to scale up, right? And at this point, they're not going to be able to fit it in a Citadel data center, so they have to start spilling over to the cloud. And literally all the user has to do is change that, change the region, maybe change the AZs if applicable, and change the count task. Now they're running at a significant scale, and they're able to run their workloads in a few minutes. Now it's pretty simple to see how you would go from cloud provider A to cloud provider B here, right? You just change the region and the AZ, and you're up and running in a new cloud provider. So I'll just sort of summarize, the status of this next generation platform at Citadel. Nomad, along with its partners Consul and Vault, are in production today at Citadel and running a wide variety of pretty significant sized workloads. Critical workloads for us. The transition from on-prem to the cloud is almost completely seamless from the point of view of a developer. They're able to run on-prem with a simple line change that you saw. They're able to move that workload to the cloud if allowed by policy. The sort of features that we liked about Nomad and what really sort of enabled us to build this system was, one, the ability to run at scale, like say 100,000 running containers is something that we do have to accommodate. The speed, as we discussed, it's a real critical feature for us. We're able to get to under 100,000 in under those 5 minutes. The ephemerality, the ability to run on things like Amazon Spot, Google Preemptive, means a significant reduction in our actual costs. And that multi-region, multi-cloud that we've discussed. And the sort of last one is touch on again, is the operational simplicity of the system. A very small, fewer than 5 team of engineers run this entire platform for the entire company. So that sort of really speaks to how simple it is to run. The bottom line, though, what it really means for the business is that those research and retraining jobs that used to run on dedicated hardware over a weekend, overnight, or run all day or something like this, now run in a general pool of compute, and they can run intraday, and the users can iterate multiple times per day, where they used to be doing that once per day. So that's what I wanted to discuss. With that, I think I'll hand it back on to Armin.
Okay, everyone, I'm actually going to take it back. Thank you, everyone, for joining us for today's webinar, and thank you to Armand and Kais for presenting. As we said at the beginning, this webinar was recorded, and we will make the recording available after processing. We will also send an email to everyone who registered for the webinar, the complete list of questions and answers after we summarize all that data. Thank you so much for joining, and have a great day.